we are going to do a really quick review of linear equations. What does it mean to be a linear equation? The line is straight. Okay, here's a graph. That is a linear function. What about the equation of a linear function? So we could do slope-intercept form. What might that equation be? This one, mx plus b, and this one could be what? Well, I mean, what's the equation for this line? We could just guess. So there are no numbers, but so 2x minus 4. That's a possibility. What does the negative 4 tell us? It hits the y-axis. That's the y-intercept. What does the 2 tell us? The slope. The 2 is positive, which means the line goes up to the right, right? As time passes from left to right, the graph goes up. If it was negative 2, then it would go down. Okay, what about the number 2? What does it tell me? Close. Up 2 over 1, rise over run. If you're going to go skiing, you got to rise before you go down the run. Now you won't ever forget it. Okay, so another way to represent a function is a table of values. So if I had x's 0, 1, 2, 3, 4, 5, how do I get the y values? Just plug them in. If I put 0 into this function, what do I get? Negative 4, okay? If I put 1 into that function, what do I get? Negative 2. If I put in 2, what do I get? 0, which you can see over here, right? If this is down 4, okay? If I plug in 3, get 2, plug in 4, 4, and plug in 5, 6. 8 would be the next one. Good job. Who are we missing today? Brandon and Kayla. We should leave a message for Kayla. Hi, Kayla. We're having a party. You're not here.
Can they hear me?
No, they can only hear me. Do you want to leave Kayla a message?
Does she really hear it?
Just talk. Yes. Just talk.
You should probably come to school.
Okay. Everybody tell Kayla that she needs to listen to this. I'll post it as soon as I can. All right, this is a linear function. Now, the x values are inputs and the y values are outputs, or also known as domain and range. And when we talk about patterns inside functions, we always talk about the outputs. So what pattern do you see in the outputs? Goes up by 2. And when we look for patterns, at least addition or subtraction patterns, we take any number and we subtract the number above it. So for instance, 4 subtract 2 is 2. So from here to here, I added 2. And if I do that for the whole chart, this is what I get. These are called the differences. Anytime you take a range value, an output value, and you subtract the number above it, you get what we call the difference. Okay? And specifically, this is called the first difference. Now, there are other differences. Excuse me. That was a double. All right. So, is it interesting to do second differences in this case? What are the second differences going to be? So if how much does this differ? By 0. So it's kind of like plus 0, plus 0, plus 0. You can keep taking differences on down the line, which we're going to do a lot of this year. But if the function is linear, the first differences will always be constant. All of the first differences, no matter how far we calculate that chart out, will always be plus 2. That's actually the definition of a linear equation, right? Every output differs from the previous output by 2. Okay, that's a pretty good review of how linear works. We don't do a lot of linear here anymore. We're going to move on to more complicated equations. Okay, so that's where this worksheet comes in. So we have built a special ramp on this piece of paper, and this ramp has a ball rolling down that travels 1 centimeter in the first second. So from here, from here to here, it takes 1 second for the ball to roll 1 centimeter. Now, this is actually a real world situation. If you built the ramp just the right way and had the right ball and everything, this would work exactly like I'm telling you. Yes. Oh, can you see your paper? Just, I mean, you should be okay today. You should be fine. All right, so the way that as this ball rolls, every second it's going to travel 2 centimeters further than it did the second previous to that. So if the first second it travels 1 centimeter, in the next second it's going to travel 2 more than it did last time, 3. So the distance from 1 second to 2 seconds is 3 centimeters. Cambry, you got that? Okay. How far has the ball rolled overall? Yes. 4 total. Okay. In the next 1 second interval, how far is it going to travel? 2 more than last time. 2 more than 3, which is 5. So it travels 5 for a total of 9. In the next 1 second interval, it will travel 7 for a total of 16. And the last 1 second interval, 9 for a total of 25. So there's a table of values below, and I'm just going to write mine off to the side because I don't have room. So we have at the end of second 1, 2, 3, 4, and 5. And then total distance. So these are seconds, total distance, and then interval distance. Can you what? Does it go to up to... Oh, sorry. 6, 7. We'll keep going. Thank you. So the total distance is 1, 4, 6. Nope, I messed it up. 1, 4, 9. 16, 25. And the interval distance is an additional, so 1, 3, 5, 7, 9. How far is it going to travel in the next 1 second? If the ramp kept going, it would be 2 more than it was last time, which is 11 for a total of 36. And if we went 1 more second, it would be 13 for a total of 49. So we already are at 25, and the next second it will be 11 more, which is 2 more than it was last time. So we went 9 centimeters in that second. Every second is 2 more than the previous second. So 11, and we take that 11 and add it to 25 to get 36. And then 36 plus 13 is 49. Okay? So this would be our X list, and this would be our Y list. Okay? Do you see any patterns in the total distance column? Are those numbers significant at all? And what do we call timesing by yourself? squaring. That total distance column is just the square of the seconds. Have you figured out why we call it squared?
Oh, I see what you did there. I actually see what you're talking about.
So let me point that out for those of you who don't. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared and 7 squared all work. Now, this actually would work if the ramp was the right steepness. You could actually build this, and the size of the ball also has something to do with it. But this is a real pattern in real life that will happen. Now, once the ball speeds up and air resistance comes into play, that messes things up a little bit, but we just pretend that doesn't happen. Okay, so we now know that the middle column is just the square of the second. So how far will the ball have traveled after 10 seconds? What's that? 100 centimeters. What about 20 seconds? Not 200. What's 20 squared? 400. 20 times 20 is 400. Have you ever figured out why we call it squared? So if I had a square has 4 sides, right? But if one of the sides was 3, then 3 squared would be the area of a square that's 3 by 3, which is 9. Okay, what if I had a square where the side length was x? What would the area be? X squared. That's where it comes from. X times x is x squared. So x squared is the area of any square with side length x. That's where the term squared comes from. Square has 4 sides, and a squared is actually raised to the second, which is a little confusing, but that's why it works. Okay, so we found out that pattern. The middle column here, the total distance column, is just the square of the seconds. What about the interval distance column? Do you notice a pattern there? It goes up by 2. So what you're saying is, if I put a bunch of plus 2s out here, then this interval distance column is linear, right? So the amount traveled in any 1 second interval is linear. Okay? Well, if we were to graph that, it would look like this. What if I were to graph this column? Would it be linear? No, it's actually going to look kind of like this. What sort of equation is that? Okay, you're not sure. Well, you don't know anyway. I was just going to see if somebody's going to throw out the wrong answer. It's certainly not linear. Why is it not linear? It's not straight. Okay. What about it makes it not straight? Why does it curve? Okay, but the linear one's also going higher. So why is this graph curved? There is a pattern. It's 2 more than it was last time. So it's not a constant number. We would say constant. If the pattern is constant, then it's linear. But in this case, we're speeding up, basically. As that ball rolls down the ramp, it's going faster and faster and faster, which makes it travel more and more ground each second. So this line is straight because the amount we travel for any second increases at a constant rate. But because we keep speeding up, this graph has to curve up. Is it ever going to stop curving up? No, it's going to. Is it ever going to be straight up and down? No, it's going to continue getting steeper and steeper and steeper. And it won't ever circle back because we're talking about time, right? Yeah, no circles. Okay, so whenever you take a function and you do the subtraction thing, we call those the first differences. So watch this. let's do 4 minus 1 is 3. 9 minus 4 is 5, and so on. These are the first differences. And we learned if the first differences are if the first differences are constant, then the function is linear. But in this case, they're not. So this list over here we call the second difference. If the second differences are constant, then it's not a linear equation. It's an x squared equation of some sort. Now, x squared, so linears look like this, mx plus b, or in the math world, they kind of do ax plus b. If the second differences are constant, then we get ax squared plus bx plus c. Now, this is the most simple of all x squared equations. It's just x squared. We call x squared equations quadratic. Why are they quadratics? Because they represent squares, and squares have 4 sides. It is. So it's kind of confusing. A squared is an x to the second, but we call the equation a quadratic, even though the exponent is 2 and squares have 4 sides. So quadratics are by far the most important thing you're going to learn this year. Okay, they're never going to go away. As far as you go in math, you will always be dealing with quadratics. And in the real world, we don't hit quadratics very often, but they lead us into larger polynomials, and those larger polynomials allow us to do everything we want to do. So these are kind of the simplest version of polynomials that we can study that have all the attributes we're looking for. Okay, so I have a triangle up on the wall, and well, I'm going to write some of those numbers down. Hang on a second. So here's that triangle. Now we're going to look at the diagonals on this triangle. This diagonal right here, going down the ones, that is constant. It never changes. Okay, if we were to graph that, it'd be really boring. It would be a flat line. Okay, the next diagonal is linear. Right? It goes up by 1 every time. Okay, the next diagonal, if I look, to go from here to here is plus 2. The next one is plus 3, plus 4, plus 5. So if I were to write that list out, 1, 3, 6, 10, 15, my first difference would be plus 2, plus 3, plus 4, plus 5. Is that linear? No, because my first differences are not all the same. But if I look at the second difference, so this is plus 1, plus 1, plus 1. So this diagonal here must be quadratic. It can be represented by some x squared equation. Okay, let's look at the next one. So if I look at this diagonal, 1, 4, 10, 20, 35, 56. So these are my y values. So plus 3, plus 6, plus 10, plus, did I mess up? 3, 6, 10, 15, 21. It's not linear. Let's check to see. So these are first. Let's try our second differences. Plus 3, plus 4, plus 5, plus 6. Nope. But if I do it one more time, so third difference is plus 1, plus 1, plus 1. So this line must be an x to the third equation. So if I go back here, an x to the third equation would look like this. Ax to the third plus bx squared plus cx plus d. And then you could go on. This next one would be an x to the fourth, and this would be an x to the fifth, and that would be an x to the sixth. And these are called polynomials. So these are polynomials. Okay? How big can polynomials get? In fact, bigger than huge. There are infinite polynomials out there where they go on forever.
So it's just what big numbers, triangles of numbers.
Well, the triangle is just sort of an example, but what we do is there's a pretty easy way to find out if you have a graph that's kind of terrible to work with. Let's say you're trying to graph that, and the actual graph is really complicated. You can create an infinite polynomial that exactly duplicates that. But there's no computer that can hold an infinite polynomial, right? So what you do is you just decide how accurate you want to be. So if you decide that that's close enough, then your polynomial might only have 4 terms. It might be an x to the 4th. But if you decide that your polynomial needs to be more accurate, so let's say you want it to be a little bit closer, but being totally perfect doesn't matter, then that might be an x to the 600 polynomial. But if you decide you need to be really accurate, maybe you do x to the 1 million, or x to the 10 billion, or something. Right? You just decide how accurate you want to be, and that determines how long it needs to be. And eventually, you just cut it off and say, I'm done. So the study of polynomials is very, very important because you can model anything you want with a polynomial. Even if you can't model it, you can get close enough that you stop caring. You can get so close that nobody can tell the difference. And mathematics on polynomials is way easier than mathematics on non-polynomials. So now, sadly, most of you will probably never get to that stage where you actually find out how to do any of that. But that's where the math is headed. So these are polynomials. This is a quadratic. That's what we're going to study. It's sort of the simplest polynomial that really does us some good. Now, linear equations are polynomials. In fact, the number 6 is technically a polynomial. But once you hit quadratics, you start to be able to look at things that you can't look at before. So this whole idea of quadratics is never going to go away. We're going to build them. We're going to take them apart. We're going to look at the different parts of them. And quadratics are extremely important. They will do you a lot of good. Okay, so you have 4 questions. First one. Yes, what is the equation? Y equals x squared. Easy. That is the first question, yes. Second question. What pattern do you see in the interval distance column? So this column right here. This is linear because the first differences of that column are constant. Okay. What is the equation for that linear set? Do we know where it would hit the y-axis? Do we know how much it's going up? We know how much it's going up. So it's got to be y equals 2x because we're going up by 2. What would the intercept be in order to fit? Y equals 2x. So the first answer at 1, the answer needs to be 1. So 2x plus 1, if you plugged in 1, you'd end up with 3. 2x plus 1 is 3. We want 2x something equals 1. 2x plus 0 would be 2. Subtract 1. So that equation is 2x minus 1. And then that way, when you plug in 1, you get 1. When you plug in 2, you get 3. So that is the equation there. Okay, third question. Oh, no, those were the equations. Okay, those are the answers. All right. Hopefully somebody tells Kayla to watch this video.